All right, welcome back. In video one, we work with variables, constants, formulas, inputs, and outputs. In video two, we work with rates, unit rates, absolute change, relative change, and percent change. In video three, we are going to focus on something called scientific notation, scale, and estimation, among other things. Scale and estimation terms, right? So scientific notation has the form of a times 10 to the nth power, okay? Where 1 is less than or equal to a is less than 10. So when you're in scientific notation, it must be written as 1, or excuse me, a must be written as either equal to 1 or greater than 1, but less than 10. That's essentially what this means, okay? So anytime you're in scientific notation, it must understand that it must be greater than 1, excuse me, it must be equal to 1 or greater than 1, which is what this symbol means, and it must be less than 10, okay? It cannot be 10, it must be less than 10, okay? So a is the coefficient, n is the exponent in this scenario. So an an order of magnitude, right? The power of 10 giving approximate size, we'd say, let's just say 10 to the third, 10 to the sixth, 10 to the ninth, right? That represents increasingly larger orders of magnitude, right? Okay, so the order of magnitude is the power of 10 that gives the approximate size of the quantity, all right? A scale factor is the multiplier connecting a representation to reality. An estimation is an approximate calculation used to judge size of a quantity, or the approximate size of a quantity. Dimensional analysis is a method that tracks and cancels units. Okay, so it allows matching units essentially to cancel. Right. Let's look at example number one. So example number one, it says write 8,300 and 0.000045 in scientific notation. So for 8,000, or excuse me, for 8,300,000, we're going to move the decimal 6 units to the left because you got to think the decimal is essentially here. So I'm going to rewrite this 8,300,000. Decimal is located here, right? Because I know that I don't have any cents. I'm going to move it 6 places. 1, 3, 4, 5, 6. So putting it there, 8.3 gives me what I want up here, which is that number that is less than 10, but greater than 1. So I moved it 6 places. So I'm going to write times 10 to the sixth power. So the number of spaces you move becomes the exponent that you need. Now let's consider 0.000045. Okay. Because we move the decimal to the right, right? We're moving to the left. Because we're moving it to the right, it's going to be a negative exponent. So we're going to move it 1, 2, 3, 4, 5. That would put it, that would give us our number that's between 1 and 10. And then I move this 5 units. So that would be a -5. So our answers are 8.3 times 10 to the 6th, and then 4.5 times 10 to the -5th power. All right. Example number two. Compare orders of magnitude. Compare 2.5 times 10 to the 8th and 4.0 times 10 to the 6th. Okay, remember this is 2.5 times 10 to the 8th power, and then this is 4.0 times 10 to the 6th power. Okay, those carets just simply mean raised to that power. Estimate how many how many times larger the first one is. So we want to estimate how many times as large the first quantity is. So what we do is we essentially divide these two together. So we're going to divide these two from one another. We can separate the coefficients and compare powers of 10. So what I'm going to do is I'm going to rewrite this. I'm going to say 2.5 times 10 to the eighth divided by 4.0 times 10 to the sixth. Again, when you're multiplying fractions, you can simply separate these two. So 2.5 divided by 4.0. And then remember, when you have exponents and you're dividing them, you can actually subtract the exponents. So you want to subtract the numerator from the denominator, and that's essentially me using a to the power of m over a to the power of n, which basically says a to the power of m minus n. Okay, that's one of those exponent rules for that particular scenario. Now, when you divide these two, you'll end up with 0.625. Subtracting these exponents, you end up with 10 to the power of 2. Now, it's important to note that this is 100, right? So this is essentially 0.625 times 100. When you multiply that by 100, you're going to end up with 62.5, right? 62.5. So what we have to do is we have to say essentially this right here, 2.5 times 10 to the eighth, is approximately 62.5 times as large as this value. Okay. So 2.5 times 10 to the eighth is essentially this much larger as 4.0 times 10 to the sixth, right? So the exponents also tell us immediately that the first quantity is on a much larger capacity, right? Because 10 to the power of eighth is greater than 10 to the power of 6. So we already know that it's greater, but we just don't know how many times it's great. All right, so a map uses the following. You can pause the video and try this on your own. So a map uses, 1 centimeter equals 12 km. Okay. So 1 centimeter is equivalent to 12 km in this particular map. Okay. Find the real distance represented by 7.5 kilometers. Okay. So we're going to use what is called dimensional analysis. Dimensional analysis is taking that 7.5 cm and we're going to multiply it by the unit rate. So 12 km over 1 cm. Okay. By doing that, notice, remember, this is the unit rate. So those cm's are going to cancel. When those cm's cancel, that leaves me with 7.5 times 12 km, which ultimately is 90 kilometers. Okay, so therefore, 7.5 centimeters is the equivalent of 90 kilometers. So the real distance is that. Let's continue. Example number 3, estimate before modeling. Okay, so estimate the number of gallons used by 20,000 drivers who each use about 12 gallons per week. Okay, so what we want to do is we want to multiply 20,000 drivers to 12 gallons per driver, right? There's that unit rate again, right? So the unit drivers cancel, right? So then we're left with 20,000 multiplied by the 12 gallons, and that's going to give us 240,000 gallons a week, right? And essentially, yes. Okay. So I was making sure I didn't miss anything. Now, so this is gallons per week. Now, we can write this in scientific notation as well. In scientific notation, 240,000 would be, remember the decimal would be here. So that'd be 1, 2, 3, 4, 5. So that's 2.4 times 10 to the fifth power gallons per week, because the problem says each driver uses about 12 gallons. Okay, so this is essentially an estimate. Example number 4, check a model result. So a calculation predicts 3.2 times 10 to the power of 12 people in one city. Use scale and reasonableness to diagnose the result. Okay, so we have 3.2 times 10 to the 12th people, okay, in one city. So first of all, we got to interpret the number, all right? So we got essentially 12 places that we need to move this way, because remember, when it's positive, it was originally moving that way. So we know that there's 12 place values behind this here. Okay, so this is essentially a really large number. Let me see. This would be millions, billions, trillion, actually. So this would be 3 trillion. Okay, so this is hundreds, thousands, millions, billions, trillions. And just to clarify, so that's 12 place values. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So that's how I know that this is 3.2 trillion people. Okay. 3.2 trillion people. So that result is not reasonable for the population of one city. 3.2 trillion people in one city, that's absolutely insane. So even if the calculator produced the value, we should not automatically accept this, right? There's no city on earth that has 3.2 trillion people in it. So the important idea is that mathematical output is not automatically equivalent to a reasonable output, okay? Math output is not logically equivalent to, okay, is just not equivalent. It's like, wait, that number is huge, but it doesn't make sense. That's how you got to think, okay? Common mistake. So a student treats 10 to the power of 6 as a unit rather than a scale multiplier. Okay, that is incorrect, right? 2.6 is a scale, it's a scale multiplier, right? Specifically, 10 to the power of 6, that's 1 million, right? Because 1, 2, 3, 4, 5, 6. Yeah, that would give us 1 million. So if a quantity is written as a times 10 to the power of 6 people, the unit is people, right? The unit is people, but the expression 10 to the power of 6 only tells us that the scale of the numerical, the value, right? So the structure is always coefficient times the scale multiplier and then times the unit. Okay, so you always want to make sure you put the unit on the end, but do not treat 10 to the power of 6 as the unit, because this is not the unit. Okay, the unit would be, in this case, the people, right? So this would be the unit, right? So in closing, the main idea for video 3 is essentially scientific notation and understanding how to write it. Okay, because you can go either way. If it's written, in scientific notation, you can know that okay, this is negative. I need to go back the other way of however many values is on the scale multiplier. If it's a much larger number, I need to go back. Excuse me, I need to go. Um, excuse me, I need to go to the left, and then over here I need to go to the right. Okay, to figure out how many place values are on the scale multiplier. So those are the big ideas that you need to understand for video 3. Okay, again, I appreciate you watching, and make sure you complete the assignment that corresponds with this video. Thank you again for watching.